Hello everyone, I'm Tarun, machine learning enthusiast and avid Kaggler. In this episode, we're going to cover how to flag insincere or hateful questions on Quora using deep learning. I'm gonna talk a little bit about the problem we're trying to solve and the key challenges we're going to face while trying to solve the problem. Okay, cool. So, first of all, the problem we're trying to solve is called insincere question classification. So basically, I'm sure most of you must have heard of this question answer website called Quora. Quora is actually an excellent place for you to find answers to several of your questions, whether it's related to science, politics, or any other field. But one of the biggest problems with Quora has been insincere questions. So usually people ask questions on Quora with the intention of getting an answer to their question. These are called sincere questions. These are people who actually have doubts regarding something and want their doubts clarified on this platform. But some people, on the other hand, ask questions which they don't really want the answer to. They're actually asking these questions to make a statement or to spread some sort of propaganda. These are called insincere questions. Insincere questions usually propagate some sort of stereotype or extreme view against a certain group of people, or tries to underscore a certain specific opinion in a very assertive way instead of trying to ask a question. So the task we are faced with now is how do we build a machine learning model that takes in a Quora question and automatically flags it as sincere or insincere. This is an important problem because people literally post millions and millions of questions on Quora every week, and no single human can actually go through these questions and take down these insincere questions. So that's why we need a machine learning model that can work at scale, go through millions of questions and take down these insincere questions to make Quora a more useful and inclusive platform. So the problem statement is we have a certain Quora question. Okay, let's say this is a question, right? And we want to pass this into a machine learning model, right? We want to pass the text of this question into a machine learning model, and it's supposed to give us a 0 or a 1. It's a binary classification problem. 0 here represents a sincere question and 1 represents an insincere question, right? So how do we go about building a machine learning model that takes a question and tells you whether it's sincere or not? Luckily, we have a massive labeled dataset on Kaggle called the Quora Insincere Questions Classification dataset. So back in 2018, there was a competition hosted on Kaggle called Quora Insincere Questions Classification, obviously hosted by Quora. And in this competition, Quora gave approximately 1.3 million Quora questions from their website to the participants. And out of these 1.3 million questions, approximately 93% were labeled as sincere questions and approximately 7% were labeled as insincere questions. So there were 93% zeros and 7% ones in the dataset. And this dataset was completely annotated using either humans or machine learning models developed by Quora. So participants were able to leverage this massive dataset of more than 1 million insincere questions to build their models. So as you can see here, since we have so many sincere questions, we have more than 1 million sincere questions probably, and the number of insincere questions is actually much smaller than this, right? The number of insincere questions is actually much smaller than the number of sincere questions. And this is a problem because if you've done any sort of machine learning or classification problems before, you know that data imbalance is a big problem for machine learning models. If one class is overrepresented and one class is underrepresented, then the model is automatically biased once it's trained because it does not have adequate exposure to both classes of data, and that's why it's unable to detect the underrepresented class. So to tackle this problem of data imbalance, we usually use some sort of data imbalance correction methods, such as generating fake data with GANs, or some sort of generative network, or weighted sampling. Weighted sampling. But luckily for us, in this data set, like I said, we have 1.3 million total questions. So even 6 or 7% of this is a pretty big number. So luckily, we may not have to go through the pain to actually explicitly handle data imbalance. And if you watch my previous video in which I went about detecting skin cancer from images, you would have known that there were only 600 positive samples in that data set, which is a very small number for a neural network to train on. But in this data set, we have thousands and thousands of insincere questions, and that's why our model should be able to get good exposure to both classes. So that's not a big problem. So how are we going to go about building a model to solve this problem? So we're going to be using a model called Roberta. Okay. So you can think of Roberta as a general purpose language modeling toolkit, and all it does is it takes input text, right, and it outputs some sort of features. So if we have the Roberta model here, it takes some sort of text. Okay, this is the text, goes into the Roberta model, and the Roberta model gives us some sort of latent vector representation of that particular text, right? And this vector is 768 dimensional, which means it takes some text, it tries to understand the meaning of the text through a bunch of different transformations, which I'm going to talk later in this video, and it comes up with a 768 dimensional latent representation of that text. And these 768 numbers are actually supposed to represent the entire context and meaning behind this text. So if we can manage to train this sort of a general language modeling framework on our specific task, we should be able to end up with a model that classifies insincere questions. So before we go on to how exactly we're going to use Roberta to solve the problem of insincere questions classification, let's get a little bit of context about how Roberta works and how it was built. Okay, so Roberta belongs to a larger class of language models called transformers, right? There's a lot of maths behind how transformers work, but in this video I'm just going to try to keep it short and give a sort of intuition about how they work, right? So transformers use this mathematical mechanism called SelfAttention, right? SelfAttention. And this is actually the key innovation behind how transformers work. If you give a transformer a certain sentence, right? For example, my dog is lazy and it crossed the street. This is just a random sentence, it doesn't need to make sense. So if you look at this sentence carefully, right, to a human it's very easy to be able to interpret what the sentence means, right? For example, if I took the word it, right, how do you know that the word it refers to dog? Because when I say my dog is lazy, when you say my dog is lazy and it crossed the road, how do you know that it refers to dog and it does not refer to street? The answer is attention. So when a human sees some text, the human is automatically able to understand the context behind a certain word and understand which other words are associated with that word. And that's what self-attention does. So self-attention takes a bunch of words, right? Takes a bunch of words, and it's able to make the model understand the context behind each word and how the surrounding words affect the meaning of that word, right? And there are a bunch of different complicated matrix multiplications and operations behind this. But to get an intuition behind how it works, just think of it as a sort of mechanism that tells the model which words to pay attention to. So when the model is scanning through the word it, it knows that it has to focus on dog and link it to dog and not street. So the model learns these representations and links within the sentence, and that's what allows it to gain a deeper understanding of language. Okay, so now since we understand what self-attention is, think of a transformer as this sort of massive deep neural network with a bunch of blocks in it. Okay, bunch of blocks, and these blocks are built around self-attention, right? So it's basically just a bunch of self-attention and fully connected layers which are continuously lined one after the other. And these blocks of self-attention and fully connected layers are called encoders, right? So you can add several encoder blocks in succession so that the model is able to get a more deeper context and understanding of the text. Okay, so now since we understand what transformers are, which is basically just a bunch of encoders built around self-attention, let's understand one of the most famous transformers around called BERT. Okay, so as you know, most language models, what they do is they look from left to right or from right to left, or they look at them both separately. Like if I have my name is Tarun, a general language model would look at my and then name, then is, and then it will finally look at Tarun, right? Or it will look the other way around. What BERT does is it looks at all these words at the same time. It doesn't go through them sequentially. It looks at them at the same time. It doesn't have any specific direction of reading the text. That's where the B comes from, right? The B in BERT stands for bidirectional, which means it actually doesn't really have any specific direction, right? And the ERT stand for encoder representations of transformers, which is basically what I explained before, right? So the way BERT was trained is they gave it a huge corpus of text from various websites across the web. They just crawled text from the web, okay? And they took all these sentences, right? And they randomly covered these words, certain words from the model. So they took 15% of all words in the corpus and they just kind of masked them, right? The technical word is masked, which basically means they covered them from the model. And basically what they asked the model to do is, okay, based on all the 85% of words available in the corpus, predict these 15% of the words. So it's given a sentence of, let's say, 5 words, and one word is just covered from it. Based on the other 4 words which it's able to see, it has to predict this one missing word. This is called MLM, masked language modeling, and it's a very common pre-training objective in NLP today, and it gives the model a way to understand the context behind words and which words generally appear in which contexts, right? So this is one of the objectives on which BERT was trained. Another objective is called NSP, next sentence prediction. So another way the researchers at Google Brain trained BERT was they gave sentences, right? They gave sentences. Let's say we have a paragraph of sentences, right? Like let's say 5-6 sentences. And what the model is given is a pair of two sentences. Okay, this is sentence 1, sentence 2. Okay, in some cases, actually in 50% of the cases, the second sentence is directly following the first sentence, which means the second sentence comes directly after the first sentence in the passage. The other 50% of the time, the second sentence is not linked to the first sentence. So the first sentence is taken from somewhere in the beginning of the passage, second sentence is taken from somewhere else, maybe somewhere towards the end, right? And the model is asked to predict a 0 or a 1. 1 represents yes, the two sentences are subsequent, that means sentence 1 comes before sentence 2, right? Or 0, these sentences are not linked, right? So training on this kind of a objective like next sentence prediction gives a model an understanding of the flow in text and human language, right? Because it's able to understand which sentence comes after the other. And in that way, it's able to kind of get a better understanding of how human language works and how we make sentences, right? Like, for example, if I have, my name is Tarun, I have a dog, its name is Rahul, okay? Something random, right? So a human would know that the second and third sentences are subsequent, right? So my name is Tarun, right? I have a dog, okay? And his name is Rahul, okay? Something random. So a human would know that the second sentence has to come before the third sentence. These two come one after the other. But a language model doesn't know that. So if you're able to teach the flow of how sentences go one after the other, you're giving it a better understanding of language. So Google basically built this massive neural network with a bunch of encoders, a bunch of self-attention layers and fully connected layers in one massive stack. And they trained it on NSP and MLM to get this massive pre-trained model which can generalize to new tasks. So this is called fine-tuning. BERT is not made to solve one specific task. It's a general language understanding model which can be applied to several different tasks. It can be applied to question answering, text classification, etc., right? So that's why we're going to be using a BERT based model today, because BERT, when it was released back in 2018, was literally the state of the art in almost every NLP benchmark, from text classification to question answering, etc., etc. So in 2019, Facebook AI research came up with this model called Roberta, which is directly based on BERT. So Roberta is basically a more refined version of BERT. So what Facebook did is they took BERT, okay, and they completely removed the NSP pre-training objective. They completely removed the next sentence prediction objective, and they only trained it on masked language modeling, only MLM, right? And they also trained it with much more data than BERT. These were two of the major changes that Facebook used in Roberta. They trained it on much more data than BERT, and they completely removed the next sentence prediction objective. And along with these, they made a host of other small changes to BERT to boost its performance. And it actually beat BERT and several other state-of-the-art models in 2019 on multiple benchmarks. And Roberta has also been proved to be an excellent fine-tuning option, which means you can just take Roberta and apply it to any of your downstream tasks because it is a general language model. And that's why we're going to be using Roberta today for our text classification problem. So how exactly is our modeling pipeline going to look with Roberta? We're going to have some text, right? The question text. Qt, and we're going to input it to Roberta. We're just going to call it RB here, right? Question text goes into Roberta, right? And Roberta is going to output a vector containing the context and meaning of that question. Like I mentioned before, all these transformers like BERT and Roberta are just a bunch of several subsequent encoders built around self-attention and fully connected networks. Roberta basically just takes this text that we have, it passes it through all these self-attention plus dense blocks, and it gives us this massive 768 dimensional vector with the entire context and meaning behind the question, right? And what we're going to do with this is we're going to build a simple dense head on top of this latent representation, right? So we're going to pass the question through Roberta, get some sort of latent representation of the text, pass this through a fully connected dense layer. I've written it as FCDL here with exactly one neuron, right? Why do we need one neuron? Because we want one number, which is the probability of the question being sincere or insincere. And then we pass this through a sigmoid layer, right? A sigmoid layer. Sigmoid is basically the simple function that takes the output of the one neuron dense layer and squishes it into a probability between 0 and 1. A probability between 0 and 1 is basically the simple function. I'll just write it down here. Equals 1 by 1 plus e to the power minus x. So this is the sigmoid function I've written down here. It takes x, which is any random real number, and it squishes it between 0 and 1. So that's it. That's the full stack that we're going to build. We're going to have the question text, which is passed into Roberta, right? And then a dense layer followed by sigmoid. And as we know, Roberta is excellent at dealing with fine-tuning tasks like this, where we have a general language model and it's able to generalize to a downstream task like ours. So now, since we have a better understanding of how we're going to build our pipeline to solve this problem, let's get straight to it.